Welcome to the second part of the video about substitution method. On the previous video, we discussed how to pick the u, which is the inner of a composition function. Now, how can we deal with an integral where there is no composition function? So, for example, we have the following problem taken from Stewart book. We have integral from 0 to 1 of e to the z plus 1 all over e to the z plus z. And we don't see any particular composition function on the integrand. Okay, so how can we pick the u? Okay, let's give it a try. So we have two obvious choices, either to choose e to the z plus 1 or choosing e to the z plus z. Let's try both of them and we will discuss the benefit of choosing each of the numerator or the denominator. Okay, so if we pick u equals e to the z plus 1, then the u is e to the z. If we pick u equals e to the z plus z, then what is our du? The derivative of e to the z is itself, and the derivative of z is 1. Okay, so now the second criteria to find the right u is whenever you pick a u and you take the derivative of that u, then the result of that derivative must belong to the integrand. What I'm trying to say is that this ez plus 1, we can find this e to the z plus 1 somewhere in here, right? If we choose this u equals e to the z plus 1, we have the u equals e to z, which is also appears there, but we don't have that z on that expression. So instead of choosing u equals e to the z plus 1, we choose our u to be e to the z plus z. Okay, so let me repeat again. We make this choice. Why? Because when we take the derivative, we have this expression which is also appears on the integrand. Right? Let's move this to the other side. Okay, so now let's continue. So we have integral from 0 to 1, and our u is e to the z plus z, which is on the denominator, and we have e to the z plus 1 dz. I forgot the dz over here. Okay, let us emphasize that this 0 and 1 is the limit for the z variable. E to the 1 over u multiplied by e to the z plus 1 dz, but we can see that e to the z plus 1 dz is exactly du. So this integral is equal to the integral from z equals 0 to z equals 1 of 1 over u, and this whole expression is equal to the u. Let me write it in yellow. Okay, so now what we need to do is to change the limit of integration. Remember that this limit of integration is for the z variable, and we want to change the limit integration into the limit of integration for the u variable. So recall that our u is e to the z plus z. When z is 0, plug in z equals 0 there, we have u equals 1. And plug in z equals 1, we have u equals e to the 1, which is just e, plus 1. Therefore, our integral equals, so now instead from 0 to 1, our integral is from 1 to e plus 1 of 1 over u du. Now what is the antiderivative of 1 over u? The antiderivative of 1 over u is natural log of absolute value of u, and then we evaluate at e plus 1 and at 1. So we have natural log of e plus 1 minus natural log of 1, but natural log of 1 is 0. So we just have natural log of e plus 1, and we are done. Okay, let's look at the next example. Integral of arctangent of x over 1 plus x squared. Similar as what we did before, if we pick u equals arctangent of x, then du, what is the derivative of arctangent? It's exactly 1 over 1 plus x squared dx. And we can see that we have the same expression 1 over plus x squared on the bottom like on the integrand, similar. Okay, so that indicates that we are on the right track. So let's keep that u equals arctangent of x. Okay, it is already a good choice. Okay, so we have integral of that arctangent of x is our u, and the rest is 1 over 1 plus x squared dx. But 1 over 1 plus x squared dx is exactly du. So this integral is nothing but integral of u du, where du is 1 over 1 plus x squared dx. So therefore, we have 1/2 u squared plus constant, and we need to substitute the arctangent back, 1/2 arctangent of x squared plus constant. So the method that we discussed earlier on the first video, and also the method of choosing the u such that the derivative appears on the integrand, is working on most of the problem, but not for all the problem. There are some problems that require our creativity, our ingenuity to tackle the problem. So this is one of them. Okay, if we try, we don't see any composition function. Well, maybe there is, for example, this x to the fourth, but there is no such obvious composition function here. And also, if we try to use the method that we discussed earlier, so if we pick u equals x, then du is dx, and we don't see any 1 plus x to the fourth here, so that is not a good choice. Now on the other hand, if we try to choose u equals 1 plus x to the fourth, then our du will be 4x cubed dx, and we don't see any 4x cubed either over here. So both of them are bad choices. Okay, so what should we choose then in this situation? Okay, well, as I said earlier, that this problem required some ingenuity, requires some creativity, and there is no recipe to do that. Probably after you try several times and then you get an aha moment that actually you need to do in this way or in that way. Okay, so I cannot tell you how we can come up with this, but notice that we can rewrite x to the fourth as x squared squared. Okay, and then we can choose our u to be x squared. Okay, now if we choose our u to be x squared, then the u is twice of x dx, and that fit into another requirement, which is x dx already appears on our integral. Okay, so this choice of u is a good one. Okay, so let's see, we have integral on the bottom, we have x squared, which is u, so u squared, and then on the top, so we need to somehow rewrite x dx in terms of u. Now we can see here we can solve for x dx. X dx is nothing but, so to solve for x dx we divide by 2 to get half of the u. So replace that x dx by half of the u. I can put the 1/2 in front of the integral and the u on the top. But now we recognize this integral. The entire derivative of 1 over 1 plus u squared is arctangent of u. So this is equal to half of tangent inverse of u plus constant, and then 1/2 tangent inverse. We want to have the answer in terms of x, put back u equals x squared plus constant. Okay, let's look at another example. This one also required some ingenuity and creativity. So if we pick 1 plus x as our u, then in our du we don't see any 1 plus x squared, so that's not a good choice. Also, if we pick u equals 1 plus x squared, we have du equals 2x dx. Okay, so we don't see any 1 plus x on this derivative, so that's also not very good. Okay, so how to deal with this problem then? So notice that we can split this integral into integral of 1 over 1 plus x squared plus x over 1 plus x squared dx. Okay, by the property of integral we can write this as two integrals. Okay, we already knew that the antiderivative of 1 over 1 plus x squared is tangent inverse. So now we can see that this substitution is helpful for us not to do this whole integral but only to integrate this integral. Okay, so we have keep the arctangent of x plus, so the u is 1 over 1 plus x squared, so that is u on the bottom, and we have x dx on the top. So we need x dx in terms of u. But now if we solve for x dx, we have x dx equals half du. Okay, So again, keep the tangent inverse and then replace that x dx by half du. We can put the 1/2 in front of the integral and du over u. So now basically this is the antiderivative of 1 over u, which is what? Which is natural log of absolute value of u plus constant, and then as usual we want the final answer in terms of u, completely in terms of x. So 1/2 natural log, and the u is 1 plus x squared, which is always positive, so we don't need the absolute value notation anymore. 1 plus x squared plus constant. Okay, so that's all. If we are interested to look at more interesting and challenging problems that can be solved partially or completely using substitution, please look at the next video. See you later. Bye bye.